Okay. What I'm going to try and do is talk in a lot of detail about the calculation of the mass of a real physical Higgs boson, and of course relate it to the recently being discovered one. This work is part of a program that's been going on for 6 years with Bobby Acharya and a list of other people up here, several of whom, Piyush Kumar and Ran Lu and Scott Watson, are here. We have a recent review of most of the work in the field. We tried to write a review which summarized in 30 pages everything that was done in an overview sense with a lot of details and references. Here I'm just focusing on the Higgs prediction. Bobby gave a talk yesterday on an overview of the compactification and a lot of the results, and Piyush Kumar will talk tomorrow on the dark matter part, and Ran Lu on the LHC predictions. The philosophy of the approach is look for solutions of compactified string and M theories, but we'll work mainly in M theory compactifications on a G2 manifold, but many of the results will be more general, and I'll sometimes indicate that, so it's not just special to that in many cases. We look for solutions that have the properties we want our world to have, like TeV scale physics and no contradiction with cosmology and other data, and we look for solutions with a Higgs mechanism, because that's the kind of world we're talking about if there's Higgs bosons in it. So we want it to have electroweak symmetry breaking. Then in those worlds we calculate the ratio of M Higgs to MZ. At the end I'll briefly talk about calculating just M Higgs instead of the ratio itself, but we focus on the normalized ratio. So what we found is that when we did this all ahead of time before there was any data from CERN, we found that it did predict a Higgs boson in the region of interest at about 125 GeV. The prediction holds in the M theory case, but it's more general. Lots of other approaches to string theory will automatically give it too. We make a number of assumptions in the process. The assumptions, but they're assumptions that are not related to the result itself. They're just assumptions to go ahead. Many of them can be checked independently or derived independently. So we compactify the M theory on a G2 manifold in a fluxless sector. We assume, this is now a very important point, we assume the gauge group below compactification is the MSSM gauge group. You can one by one at this point take any gauge group you want and repeat exactly what we do and get the Higgs mass prediction for it. And I'll make a couple remarks on that near the end of the talk. We make the standard sort of assumption about inflation. The Hubble parameter at the end of inflation is larger than the gravitino mass. We assume after compactification you have a supergravity field theory. We assume there's one heavy fermion in the theory. That's of course true, but it's not being derived in this framework directly. And we write the normal Kähler potentials and gauge kinetic functions that have been derived in the past in a number of papers for this compactification, and assume that they're basically not misleading us. I want to emphasize that while there are assumptions, there are no free parameters of any kind anywhere in the whole process. You don't fit anything, you don't use anything to do with free parameters, you just calculate. We'll see that there's some sensitivity to the gravitino mass. If you change the gravitino mass by 50 TeV, you shift the Higgs mass by about 1.5 GeV. And there's a mild sensitivity to tangent beta, and mu and tangent beta are strongly related by the fact that you require a Higgs mechanism to occur, electroweak symmetry breaking.
May I ask a question? If there are no free parameters, what does M3 have in tangent beta?
They're not free parameters. I'll tell you the numerical value of tangent beta in the calculation from the theory, but the calculation isn't completely accurate, so we allow it to vary a little bit. But we do a calculation from the theory, and it tells us tangent beta is 10, period. But the calculation is not yet reliable to a factor of 2 or so. Factor 2 one way, factor of 50% the other way. The gravitational mass has a lower limit, and it has a soft upper limit in contradictions occur. So the gravitational mass, the constraints are phenomenological rather than theoretical. But it's fixed before, no, we don't. We fix it by other things and then put it in here. It's the lower limit, for example, is fixed by cosmology arguments and then kept there, and we don't have fixing the parameters not done with the Higgs mass at all. That's the point. And it has a very little sensitivity. If you look, you can think about how big it could be, but you start getting into big trouble if it's much bigger than 100 TeV. So that actually doesn't allow you much change in the prediction. But within that range, I show you the sensitivity. So, and I'll try and explain why is M Higgs coming out light. I'm going to talk about, we're all starting at the Planck scale for everything. I'll try and explain how we get from the Planck scale to 125 GeV. There's two kinds of issues there. In the first case, you go through a series of arguments like this that Bobby mainly summarized or derives. You start with a compactified M theory. You have orbifold and conical singularities in various submanifolds. You have coming from them gauge and chiral matter. That leads to gaugino and meson condensates. You get F terms, you get supersymmetry breaking, the moduli get stabilized. You're in a de Sitter vacuum. Typical gauge groups give a condensation 4 to 5 orders of magnitude below the Planck scale. That gets cubed in the superpotential. So the gravitational mass in a top-down approach, if you took it as a calculation, would come out in this 50 to 100 TeV range. So one way you could look at it is that's a calculation of the gravitational mass. You just use it from now on and don't vary it at all.
What's the definition of typical gauge groups?
You look at 100 gauge groups or so and look at their ranks, and it's the rank of the gauge group that matters for this, and then you look at the typical numbers you get, and you're normally 4 or 5 orders of magnitude. They're usually larger rank, you know they are. Yeah. So yeah, there are a few small ones, but the large ones dominate in that they cause the condensation earlier and make it happen.
So did you find that in concrete compact G2 manifolds by analyzing singularities that correspond to those gauge groups and particle spectrum?
The gaugino condensation is coming from the orbifold singularities in 3 cycles in the manifold, and those you know how to do something with, so you can actually look at literature on those. In the 7-dimensional
compact G2s.
Yes, so there are compact G2 manifolds with orbifold singularities.
So you could analyze that and obtain those results?
We haven't done, there's no systematic construction of compact G2 manifolds which provides, something like a Kreuzer-Stark database. However, there's a lot of interest in the mathematics community at the moment. I myself was a co-organizer of 2 recent conferences on G2 manifolds. There's some interesting papers coming out, and people are working on it. But
and all the people who look at that question,
orbifold singularities of G2 manifolds are, there's nothing to say that they're not there. I mean, they are there in. They're easy to get the basic example of a compact G2 manifold. The first examples by Joyce were made by looking at G2 manifolds with orbifold singularity.
Yeah. So that part is reliable and qualitatively safe to do. Then a very important point is that you relate the gravitational mass and the eigenvalues of the moduli mass matrix. And there's a very general argument, which I'll briefly sketch on the next slide. Bobby said it, but not in much detail, so I'll mention it again. If the gravitational mass is larger than the smallest eigenvalue of the moduli mass matrix, And in turn, that's larger than about 30 TeV from constraints from things like BBN. Ki-Woon showed you yesterday a lovely non-generic way to get out of that by having two late inflations very specially tuned. So you have to really work hard and be as clever as he is to get out of it. Then you calculate from those the soft breaking Lagrangian, and you find things that are historically non-typical and have different predictions. For example, large trilinears, large scalars. Of course, if the supergravity formalism, the scalars and the trilinears are approximately equal to M3 halves, and B is in the same range as M3 halves. Okay, genome masses are expected to be suppressed. Bobby went through the argument partially, and I won't take much time for it here since it's not the crucial point here. The mu term is very important for what happens. We've used an argument started in about 2002 by Witten, who wrote a discrete symmetry. Witten's discrete symmetry was unbroken, and so the mu term was identically zero at the end of his paper, which solved all the relevant problems. You can see that the Witten's discrete symmetry, which you can impose on the G2 manifold, was broken, is in general broken by moduli stabilization because you can't move the matter around then. And so we can make a qualitative statement that the effective mu parameter, it'll be proportional to M3 halves because it should vanish when supersymmetry breaking goes away. And it's proportional to the moduli valves divided by M Planck. So it's suppressed from M3 halves by an order of magnitude or 1.5, because that's what you typically get for the moduli valves. So here we're just making an estimate of mu that should go along with the rest of this theory. Then you find that at the high scale, all of the soft terms of the Higgs sector are, sorry, that's going the wrong. All of the soft terms of the Higgs sector, no, I'm not back there yet. That's where I was, okay. Are of order M3 halves. At the high scale then, everything is the order M3 halves. There is no electroweak symmetry breaking in the theory at the high scale. There's no such thing as tangent beta at the high scale. You don't have Higgses at the high scale. Then you start to run down to the low scale to calculate, and because you've generated this 50 TeV or so scale, and you run down to the low scale and you find electroweak symmetry breaking occurs. And it's mainly the quantity m squared HU that runs down. That's where all the physics activity is. I'm just mentioning here in this slide that argument about the generic relation between the lightest moduli mass and the gravitino mass. Qualitatively, it's just that when you write down, well, the derivation was done in 3 papers over time written for different purposes, and but the derivation is very firm and agreed on by many people. It's basically that moduli mix with scalar Goldstinos, and scalar Goldstinos have gravitino masses. Once there's any supersymmetry breaking involved in stabilizing the moduli, you can stabilize a lot of moduli without supersymmetry breaking if you want, but if there's any supersymmetry breaking involved at all in stabilizing any of the moduli, then this argument is correct. So you write the moduli mass matrix, you don't have to calculate it. You know inside it somewhere is a complex scalar Goldstino, so a 2x2 piece of the moduli mass matrix with a mass scale of 3 halves. Positive definite mass matrices have the property that the smallest eigenvalue of the full matrix is smaller than the eigenvalue of any of the relevant submatrices, so you end up with that result. Very general for supersymmetry breaking theories. This you can clearly see it in the M-theory case, but it certainly holds in type 2 theories and heterotic theories in general. The results that you get are not going to be special to us. Now let's turn to the Higgs sector. I'm giving maybe more detail than I need, but as I've given talks over the past few months, I've found that lots of experimenters and lots of string theorists have not necessarily studied the details of Higgs sectors and such things. So you need 2 Higgs doublets for anomaly cancellation, and by Higgs mass, you mean the mass of the light as CP Eman neutral scalar. It's been known for a couple decades that if the Z boson, for example, gets its mass from the Higgs mechanism, then there's an upper limit of about twice mz on that Higgs mass if the theory is perturbative up to the unification scale. And there's an upper limit of about 140 GeV on just the MSSM, whereas the twice mz limit is on any theory that stays perturbative up to high scales. But the precise value depends on all the soft breaking parameters and comes into the formulas and how they run. I'll show you in some detail. So you can see why you start at the high scale, you run down. We'll see the condition for electroweak symmetry breaking, but when you get electroweak symmetry breaking, that's called radiated when it's from the effects of the RGE running. Then you get down to the low scale and you get it and you get a Higgs mechanism. Why the value is precisely 125 GeV is complicated because it depends on all that running and on all the soft parameters. There's no simple way to see the number 125 emerge because it's a complicated thing from several things. The Higgs potential at any scale has this form with m squared HU and m squared HD being the soft breaking terms and the soft breaking B term coming in. Then the actual mass matrix you diagonalize has this form and all the things in there run. And you have to find a negative eigenvalue if you want electroweak symmetry breaking. So the main thing that, as I'll show you, that runs is m squared HU. The quantity tangent beta that is important for the low scale theory doesn't exist until after the breaking occurs. And people normally take 2 of the vevs squared and put in the numerical value of MW, reducing the other uncertainty to that tangent beta. So it looks a little bit like this in terms of an explanation. You have a high scale compactified string theory. I emphasize the trilinears are the same size as scalars or larger because phenomenologically people didn't look at that part of the sector in the past until the string theory led to it. You get basically a result like this, that m squared HU, which remember is the quantity in that Higgs mass matrix, that takes a form like what is written there, the scalar mass at the high scale squared and the trilinear at the high scale squared, and then the term f sub m of t, that is purely standard model, calculable, known stuff. It's got top quark Yukawas, it's got stuff in it that everybody knows and knows how to calculate very well. There's no string theory or parameters in that. You calculate those, they have numerically a value of about 0.1 at the weak scale, the 2 F's, and each is about 0.1, not exactly, one is 0.1 and one is 1.05 or something close. And these guys, the string theory told you, were all about the gravitino mass at the high scale, and they stay there. So you get a double cancellation here if the trilinears and M0 are the same size approximately. First, there's the 0.1 of these terms, and second, the 2 terms cancel to a good accuracy, and you get 2 orders of magnitude suppression in m squared HU from the basic argument. Graphically, it looks a little like this. This point is down to 50 TeV. This scale is any of the masses again, and so here's 50 to 100 TeV up here. M squared HU is still running down, but the graph stops at 50, so it's way down there. When you're done, mu doesn't run much. But you can track these things and see what's happening qualitatively very well. Just for people who are experts in how you compute, you write it at the high scale, you run down, as we said, you maintain the electroweak symmetry breaking, you use a procedure called match and run, where when you get to the different stages, you stop and redefine, and you integrate out at various stages carefully. The programs like SoftSUSY should be valid in our region. We're using masses up to about 50 TeV. Those programs are known to have big trouble as you get above 100 TeV numerically. and you have to do special things, but in the region of 50 they should work. So we do it by hand with the match and run, matching at the square root of the mean of the stop masses, using two-loop RGEs, etc. We do it as accurately as any of the studies in the literature in the past year on these kinds of subjects. The main sources of imprecision are that a 1 GeV uncertainty in the top mass gives you 0.8 GeV uncertainty in the Higgs mass. So you cannot beat that until the top mass is better measured. There's a similar result for alpha strong, about half as strong. If you have a gluino mass that can make a range of a factor of 2 here, that gives you about half a GeV uncertainty in the Higgs mass. And the trilinear couplings, which are calculated, but you might want to check, we just check to see what if they varied. Then if they vary from about 8/10 of to 1.5 times the scalar mass, they give also about a half a TeV uncertainty, half a GeV uncertainty. These are the largest sources of uncertainty in a precise Higgs mass prediction. So again, the basic argument from a slightly different point of view, you start by assuming that you have a supergravity field theory limit. The squarks are greater than about 30 TeV. Then you assume again the MSSM below the compactification scale. The main scalar that varies is m squared HU, m squared HD doesn't. You keep asking for solutions that have a Higgs mechanism. That's the world we live in. We find many and we don't care about others. I'll show you the tan beta argument in a little more detail in a minute, but 10 is the central value. Then your supersymmetric Higgs sector is called the decoupling one because all the other Higgs states, there's 2 Higgs doublets, so there's 5 mass eigenstates. Only the one Higgs is light, the others are in the same 30 to 50 m gravitino mass region. And then you finally, I'll show you the graphs in a minute, get this prediction, and you also predict that the Higgs itself should behave like a standard model Higgs particle. Its production cross-section and branching ratios deviate very little. A few percent, maybe up to 10% deviations are okay for known reasons from other superpartners. The tan beta point to make is here. The usual electric symmetry breaking conditions that all of you saw at some stage in your life in a course or looked at in some talk are these standard ones, simplified slightly for tan beta not being too small. Then if you then let m squared HU run, m squared HD and B don't, they stay about m3 halves. You take mu to be suppressed according to the argument I gave you from the Witten discrete symmetry on the moduli stabilization. Do this trigonometric approximation. B stays equal to 2 m3 halves because to guarantee no mu term in the superpotential and supergravity, you need that relationship. The bottom line is then that you can combine those to get that. And the thing you might want to remember is that what comes out of this analysis is that it's a good approximation that mu times tan beta has to equal the gravitino mass over 2. Very generally in theories with heavy scalars and supergravity, it's hard to avoid that relation. So a numerical example, if you take 60 TeV and 3 for mu and tan beta of 10, you get tan beta of 10 and having approximations, you might want to study this region to see what happens. I'm here summarizing on 2 slides the mu argument in a little more detail. Normally mu and tangent beta are treated as parameters, but of course we need to derive them in the structure of the theory to have a derivation, and we want to do that from first principles. You all know if mu is in the superpotential, it should be aborted the string scale. You need a symmetry. Witten wrote down a complicated, apparently unmotivated discrete symmetry which does the job fully of keeping mu equals 0, solving the doublet triplet splitting problem, making the lattice superpartner stable and so forth. But he did not break it. When the moduli are stabilized, then the matter effects are not invariant, so you get an effect there. It would be better to understand the details of that stabilization argument better, but qualitatively it must occur. Then mu is proportional to M3 halves, and it's proportional to moduli Bev. I said this in one line before. So you finally expect mu less than about 1/10 of M3 halves in this approach, and that affects the Higgs mass a lot, and other things like direct detection a lot. So this is the graph we posted a year ago, where we showed the whole tan beta range, but if you look in this region, you expect the mass then around 125, 126 GeV. What we had not yet included here was the full precision analysis. What's the effect of the top mass? What's the effect of the Bruino mass? How do they correlate? They're all related if you maintain electroweak symmetry breaking. So it's highly non-trivial to do that. This can be thought of as the final answer in one sense. In this graph, so I've kept tan beta now in the range that the theory says it should be. Here's tan. I've used one value of M3 halves. So you can take that as the final prediction. Here's 125 GeV, and that's 130. Here's a more detailed study of it, which is very instructive and helpful if you want to take this physics input and relate it to the underlying theory. So what this shows you, here's the Higgs mass on this scale. Here's tan beta down here. The 50 GeV region I showed you in red a minute ago is in these brackets. So here's the upper limit of it and the lower limit. If you change M3, the gravitational mass, to 100, then this is the upper limit of it. The blue dots show you the entire allowed region from scanning over top mass and Bruino mass and strong coupling and everything but the gravitational mass. So if you want a gravitational mass of 100, you take this band of blue dots and shift it up so the upper limit is there. And that gives you a sense of that scatter. That's the most that happens when you change the gravitational mass to 100. And as I said before, it goes up about another 1.5 GeV in the Higgs mass if you double the gravitational mass again. So this is the important set of results, and these blue dots all have that small mu consistent with mu tangent beta equal M3 halves over 2. Here in the red points show you what you get if you have a large mu in the same framework. Then they allow electroweak symmetry breaking to occur if you're on one of the red points, but it's only possible at small tangent beta because of that correlation. We assume the MSSM below the compactification scale. We have written models that extend the MSSM that give the same M Higgs value as the MSSM. That is, it's not unique. You can write large numbers of models beyond the MSSM or extending it that still give 125. There are other models that we've written that are generically in conflict with extending it. That is, they change the Higgs mass prediction. So studying how these models work will be very useful for pinning down what the gauge group is at the compactification scale. And right now, we don't see a full pattern yet, but we have examples of each. The implications of all this, I have 2 or 3 more slides, I think. No, a few more, but I'll go through some quickly. So I want to emphasize that this is a string theory result. You have to get these results, you have to have theories with stabilized moduli and moduli stabilized with supersymmetry breaking. You have to have that gravitational moduli connection or you just don't get these derivations. You derive soft terms instead of guessing manually because the soft terms are related precisely in the derivation. You must have mu embedded in the theory to make sense of this, and you must exhibit the stringy solutions that have electroweak symmetry breaking. And as I said, there are no parameters that change anything noticeably in the result. If you want to compare with phenomenological stuff, here's an example where I listed on this side the compactified string theory results and the kinds of results you get from split supersymmetry or lots of the other kinds of models. Here you derive the solution to the large hierarchy problem. Here you assume there is no solution, you just guess an answer. We get generic solutions with electroweak symmetry breaking. They only assume electroweak symmetry breaking exists. Gauginos are suppressed in this case dynamically. We don't have time to go into the details of that, and Bobby said something about it there. They're suppressed by an R symmetry and suppression by an arbitrary amount. In that case, since it's an R symmetry, trilinears must be suppressed also, but here trilinears are not suppressed, which is very important for understanding what's happening in terms of getting down to the 1 TeV scale. That little hierarchy problem below 50 and 1, you mainly derive by that factor of 100 running in M squared HU. I'll mention in a minute a little more about it, etc. So you can go on. We don't have any long-lived Gauginos, some of these do, and so forth. You can think of it a little bit this way, that you start at the Planck scale, and by the good old mechanisms go down to a gravitino mass of 50 to 100 TeV, then radiative electroweak symmetry breaking takes you down near the Z mass, and on the other hand, gaugino mass suppression takes you down to the 1 TeV sort of scale with lighter charginos and neutralinos. One way to think about it, if string theory were to give a successful description of our string vacuum, including the Higgs mass and gluinos and dark matter, you wouldn't really want to call string theory unnatural, though it does have these little hierarchy issues not quite solved. If you calculated the Higgs mass directly instead of the ratio to the Z, you actually would get a number with a Z mass of order 1 or 1.5 TeV if you just started and calculated. So there is a little hierarchy problem of an order of magnitude or so there. There's an interesting thing to think about in that context. Donahue et al. Argued a couple years ago that the Higgs veil can vary by a factor of a few without any change in standard model physics, and they only varied things one at a time. If you vary several, you could get larger variations. So maybe it's quite fun for me to think about getting down to the TeV scale. Maybe the Z is right in some sort of accidental way, and there's a range of values consistent with this. I like that. I like to think about that a little bit. I'm just going to briefly advertise the talks of Piyush Kumar on the associated dark matter, the 130 GeV gamma coming from annihilation of two dark matter particles to a gamma and a Z, and the talk of Ranvu about LHC. You can get a spectrum, you can get an upper limit of about 1200 GeV on the gluino mass associated with the Higgs prediction and the dark matter. So that's a strong prediction for this whole class of theories. You can look at the decays, find they have unusual signatures with different branching ratios, and an amazing thing will be disappearing charginos in gluino decays in the detector that make a very nice signature. So finally, it's great that we have data, and now for Higgs and maybe even for dark matter, and that implies in this kind of theory, this class of theories, we will soon, the Higgs and the dark matter data look like the data from Compactified, constrained by cosmology and phenomenology string theories with stabilized moduli should look. And the M-theory version, at least Compactified on a G2 manifold, has a lot of the steps you would, or the properties you would like a candidate for describing the R-string vacuum to look at, all at once without any changes in approach or parameters or anything, can give you the Higgs sector result and the 130 GeV gamma. In fact, the 130 GeV gamma was predicted 3 years ago by this approach. Not exactly the mass, but that there should be one in that mass region. You can have moduli stabilized TeV scale, gauge coupling indication. It takes care of weak and strong CP violations. It has a good argument for baryogenesis, including the ratio of baryons to dark matter, the string axion sector, no flavor problem. Many of those features are generic and will hold in other corners of string theory too, because they're dependent on having scalars and on properties like that. Thank you.
So, for your formula for the value of tangent beta, you had a formula that had a b, the b term, right? B mu, and b you said was equal to twice m3 halves. Why is it twice m3 halves? That 2 changed the value of tangent beta by a factor of 2. Why not 3 m3
Bagger
halves?
and West page something. You want the no mu term in the superpotential, and there's some constraint there. I'd have to think to give it to you more precisely, but
This
you
is
look up the
soft-
supergravity formulas, and
This super,
it's there with our normal.
this is m sugra or something, but m sugra says that b is equal to a minus 1, right?
No, that's in a very special one, that's a Peroni model or something.
No, that's also coming out of minimal sugra. B is equal to a minus
Or
1.
the Nilles
A-
review has the 2 in it.
Well, but the 2 is a model-dependent statement, no?
No. Yes.
Yes.
It's model dependent in the sense that you want no mu in the superpotential.
No, it has nothing to do with mu. Mu is supersymmetric.
We,
B
what,
is-
what we did was we have the moduli potential, and then we just calculated mu for the case when you've got Witten's discrete symmetry, and we calculated B mu. And that's what came out.
And there's
But it-
ratios too.
So it is a model-dependent statement.
In this approach to the mu.
A question about predictions. First, you say the Carino mass is below 1.2 TeV. That's for sure.
I think it's
Yeah,
pretty
okay.
close for sure.
No, just to-
We didn't check the numerical.
The other question is, when you are saying that you predicted the Higgs.
This approach predicts the Higgs mass.
Well,
And we
so-
did the calculation.
Well, okay, so can you again show the plot which you showed last August? This one. So this was the prediction. It's
It's the
somewhere
same as the
between,
red one.
yeah, it's between 110 and 128. That is what you showed in August.
Mhm.
Now this plot with the colors, you showed later. For example, when I saw this plot for the first time, I knew the rumor about the Higgs mass.
Oh, I didn't when we wrote it though. We
Well, maybe you wrote it and you kept it
So-
in your drawer for a month. But you see, I remember when this came out, I knew about the rumor. So it's not a question of whether this is right or wrong
We
with the
stand-
view, it's just a question of that the prediction should come before. That knows the result.
We had been spending the fall calculating the effects of the top mass and the Galeno mass
Yeah.
and checking that radiative electron symmetry breaking was satisfied. We did not know that there was a CERN seminar coming. We were gathering up our results. Then we suddenly heard there was a seminar coming, and it took us 2 more days to post the paper. But we'd been working 3 months after the summer. We weren't smart enough or clever enough to know ahead of time it would come. I promise you, we had not heard any rumors. We didn't change anything. Every step of the calculation is totally clear and clean. You can't change it even if you want to. So you can accuse us of anything you want, but
No, I don't
But it has
accuse
nothing
you.
to do with
This
it.
might be right, but you might be bigger in case
but-
the rumor has changed. Well, no, it's
No,
not
but in our
whether it's
paper-
right or wrong. It's just a
It's
question. When I
all-
make a prediction, I should make, this
I
is a
would-
plot. This is a plot which was the prediction.
I would have liked to make the prediction sooner, but I didn't know. I thought they were going to talk in February. I thought we had time. It turned out we didn't. I wasn't smart enough or well enough connected to figure out that we needed to do it. I apologize.
Can I just quickly comment on this? But in in a much earlier paper, we calculated mu, and it is
Yes.
smaller than
Everything was
M3 half.
calculated ahead of time, just put together.
Okay, actually, I want to ask I want to ask about sorry. Can I,
Go ahead.
Okay. Your calculation of mu parameters. You say that you have some discrete symmetry which forbid mu, and then eventually you generate it, which is proportional, which is double suppressed by gravitational mass, and also suppressed by moduli vacuum values. But does it mean that why you need, I mean, this gravitational mass carries some discrete charge?
Sorry?
This gravitational mass.
No. It's
I mean,
simply-
because you
I
say that,
didn't hear the question.
okay, because you say that the mu is forbidden by some discrete symmetry, but eventually you generate it. That means that you break the discrete symmetry by something, and then your mu should be proportional to something which breaks your discrete symmetry. That's what I would expect.
Yeah.
So then you have this moduli vacuum value times gravitational mass.
Right.
So which part breaks your symmetry?
The VEV.
Moduli.
Yeah.
That means the moduli is charged on the discrete
That's
symmetry.
right.
Oh, I see. Then why do you have that suppression by gravitational mass?
It's not suppressed
Not
by
just
the gravity.
moduli.
It's not suppressed by the gravitational mass. The gravitational mass is proportional to the gravitational mass because
Because
of the Giudice-Mazziero.
oh, Giudice-Mazziero. Okay, yeah, that's it. Okay.
That part is the same for everybody. It's the extra suppression from the way that mu is included in the theory following the symmetry that Witten wrote 10 years ago. which
What is your stop
worked.
mass? Your stop mass. Stop. Scalar top mass.
Stop mass is of order m3 halves at the gut scale.
Stop
It's-
about order 10 TeV.
Yeah.
I can show you.
And certainly your Higgs.
So the stop mass is in the green column. Sorry, the scale's not great. It's about 25 TeV.
So basically, the reason that you have 100, this relatively heavy Higgs mass, is that you have a heavy stop mass.
Yeah, but if you look at the usual formula with the logarithms and the things, then you put in the heavy stop mass.
Not surprising at all.
You can see exactly why you get what you get. Yes, correct. Yeah, there's no tricks. It's just what you see.
First, Shanta. Corey, so the value of the cosmological constant is more or less known.
Right.
So you can't make a prediction. However, can you make a post-diction?
I mean, accurate one? No.
So how much, what range of values do you have? I mean, the problem, as I see it, is that you do not even have, in principle, a way of fine-tuning your cosmological constant to 0, because you do not have a discretum, you do not have fluxes.
No, actually we do have a discretum, which is because the potential is it depends on two discrete quantities in the simplest case, which are the two hidden sector gauge groups. And there's some nonlinear function of those, the ranks of those gauge groups, which is effectively is effectively the constant in the superpotential that you have to dial in order to scan the cosmological constant. So that question depends upon the number of G2 manifolds with orbifold singularities and the distribution of this function amongst that set.
So can you estimate that? So for example, in type 2b with fluxes,
You don't even know the number of compact Calabi-Yau threefolds. Nobody knows that number.
yes, but you know that you can turn on fluxes, right?
But for fun,
So you can easily have more than 10 to the 120 configurations.
So for fun, Konstantin Babkov did an estimate of the things Bobby is listing and came up with a number big enough to solve the cosmological constant problem, but he can't defend those numbers well enough. He hasn't published them yet. But he did do an estimate like that, for example.
My question is on the gravitinomass, just to clarify. So it's set by the difference of the ranks in your Gaugino condensate in your hidden sector. So usually, I think yesterday we had an explicit formula in Bobby's talk where it's depending on Q minus P, which has to be larger or equal to 3. In order to get it to in the TV range, you set this to be 3. But I understood of yesterday's talk that this is something put in by hand, an assumption that you make that there's low energy supersymmetry in the sense that this is in 50 TeV or 100 TeV range, but there's no theoretical argument for why it has to be there. I mean, this rank difference can be 10 or something, so that brings you up the gravitinomass to an intermediate scale, up to the string scale. There's no argument, if I understood you as of now, to have it in this TeV range. So that, because that would
As I said,
We
there's
need
no
to find out.
theoretical argument that we know of.
That's a
So
bottom
far,
up
that
approach.
puts an upper limit on it. But it looks like there are phenomenological hints, but we're looking for solutions to study at this point. If someone wants to study the solutions with larger gravitational masses, that's okay. It looks to us like the relic densities and other things will go wrong, but we don't have a strong, clean argument for that at this point. You
This
should
will,
say a
this
little
will
bit
feed
about
in the
that.
Higgs mass, right?
But we don't have an upper limit.
This will feed into your Higgs mass, right? So then, if you allow for a gravitational mass much larger, you get up to 140 GeV of your Higgs mass. So then, in principle,
Well,
depending on the mu term, you have a relation that allows you
So the
115 or even 90
Higgs mass goes
GeV to
up
up to
about 1.5
200 GeV.
GeV.
So then I don't
per
understand the
meter
prediction.
as you increase.
Well, I mean, you know, if I put Q minus B equals to 4 or 5, those models are phenomenologically irrelevant. We cannot live in a universe like that. So it's like studying, you know, ADS5 cross S5 as a candidate vacuum. I mean, it's irrelevant. The other point is that that is, yeah, it's kind of anthropic. The other point is that in the simplest model that we wrote, the first model that we wrote, Q minus P equals 3 comes out automatically just from minimizing the potential. And when you additionally set this nonlinear function, you know, the constant term in the superpotential effectively to 0, you get actually 50 TeV as the scale. So the minimal model actually has it built in, but if you were to extend it into, let's say, more
Let me say
more
one
generic
more thing.
cases,
We're
then
looking for
you could have other
solutions.
Susie.
We're looking for
other
solutions that can describe our world, and we find a whole set of those with that property. And in those, that is the prediction. It looks to us like a larger value of the gravitational mass will not lead to an acceptable set of solutions to live in a world like, but we haven't proved that yet.
Okay, well, how long are we going to continue? Because
Just one
maybe-
question.
Okay.
So if we agree that your calculation of mu and B mu are model dependent, then it seems pretty reasonable that you can get a generic case where you have tangent beta of order 50. So the question is, if you allow tangent beta to go beyond 15 up to 50, how much does the Higgs mass change?
We can't find any electroweak symmetry breaking solutions with that property. If you have to look. We didn't find anything outside of that 5 to 15 range. But we're exhibiting a set of solutions. If someone can find other solutions, they
Are you
can-
taking the Higgs
they can
masses?
look. We haven't tried to prove that there are no other solutions at all.
What's the boundary condition on the Higgs up and Higgs down at your gut scale?
The scalars are equal.
Equal.
They're derived to be equal.
Okay, so that's the constraint.
Not a boundary condition, it comes out of the compactification.
Okay, Fernando?
Why do you have to assume the ratio between the Hubble scale and the gravitational mass? Why is that relevant for all these completions?
Oh, we assume for simplicity that at the end of inflation that the Hubble scale is large enough that the moduli will start to oscillate and fall under the minimum of their potentials and not be less than the gravitational mass, which can cause you trouble with issues like that. My own guess is that if you study the situation, there's no problems like that, but we're assuming that the simple picture works qualitatively and that the moduli become matter-dominate the universe soon after the end of inflation in the way you would normally expect. We haven't tried to prove absolutely. There are arguments that you're safer. There are the arguments like
It has to come out of inflation. But it has to come out of inflation.
Yeah, we don't understand how inflation works in the M theory case.
So we just assume that the normal thing happens, that the moduli start oscillating in their potential and the universe is matter dominated very quickly.
Okay, now the absolutely last question by Hans Peter.
Now, since you are all here, and since you made the prediction that the Cluedo mass has to be below
1.2 GeV. Do you agree?
No, TeV. No, so but let me elaborate on that. That depends on the.
Is this a prediction or no?
Yeah, so the 1.2 TeV comes by saying that the 130 GeV gamma line corresponds to the we know dark matter.
So then we scale
So
from
if
that.
that signal went away, if the dark matter signal went away, then you'd have a higher we know mass and a corresponding.
If that signal stays,
No,
then it's
you
a
see, for
prediction.
example, in our case, and we had the Roddy picture, we have a very similar thing, but we have a small a, rather small a, because of the suppression, and that forces us in some way for the same Higgs mass to push up the Cluino. In that sense, when I was showing, we had 4 TeV for the Cluino, where you have 1.2.
You don't
So that
have-
would be a nice way to actually distinguish between the schemes. So this is why I
But
wanted you said 1.2 TeV.
Given, but you don't have any, last word, more.
Okay.
You don't have any dark matter annihilation line predicted at all, it's observable. So if they observe any dark matter annihilation line, non-energetic gas from the heavens, then you've already got a problem. So it's a related problem. They're correlated to your.
Okay, let's close this session here and let's then go into this talk.